In this video, I'm going to discuss a fundamental result from coding theory. I'm going to show that Reed-Muller codes achieve capacity on the erasure channel. Now, what I really like about this result is that it connects this somewhat combinatorial question to really basic ideas in Fourier analysis and some deep ideas in Fourier analysis. And I think that connection is really beautiful. So let me first start by introducing error-correcting codes. An error-correcting code is a set of binary strings, and always we'll focus on strings whose length is n, with the feature that if a sender takes one of the elements of this set, one of the strings, and sends it across a channel, and then an epsilon fraction of the coordinates of the string are erased, then the receiver can decode the intended transmission just by knowing what they receive as well as the entire set of code words. Okay, so a set of code words satisfying that feature is a good error correcting code for our purposes. So the model of errors that we'll be working with is the model where every coordinate of the code word is going to be erased with probability epsilon. When Shannon first studied error correcting codes, he proved that there is a set C of size roughly 2 to the 1 minus epsilon times n that has the feature that it can recover from such errors. And moreover, you can't do any better. There's no larger set of code words. And the way he proved this is he showed that if you pick a random set of binary strings of this size, then it will recover from errors. Okay. What we're interested in doing is understanding a specific explicit code and showing that that explicit code also satisfies all these nice properties. Okay. Now, a very important class of codes is the set of linear codes. These are codes that correspond to a linear subspace of f2 to the n. Okay. And the Reed-Muller code is an example of a linear code. Every code word in the Reed-Muller code corresponds to a polynomial. And the string that corresponds to the code word is just the evaluations of that polynomial on all of the points in f2 to the little n. Okay. So the Reed-Muller code is actually exactly the set of evaluations of all polynomials of degree at most d, where d is a parameter associated with the chord. And the theorem that I want to prove is that for every epsilon, if n is large enough, then the Reed-Muller code of dimension 1 minus epsilon times n will recover from epsilon minus little o of 1 random erasures. Okay. So that's the result we're going to prove. And it turns out the result is actually much stronger. The result is not going to use anything too specific about Reed-Muller codes. It turns out that any linear code that is sufficiently symmetric will enjoy the same features. Okay. And that's really powerful. Okay. So now to explain what kinds of symmetry we need, I need a few definitions. Given any permutation of the coordinates of the code words, you can think of that permutation as mapping a code word to another string by just applying the permutation to the coordinates of the code word, like this. Okay. So now, given a code, we can talk about its group of symmetries, and this is just the set of all permutations that do not change the code as a set. Okay. So it's exactly the set of permutations pi, such that if C is in the code, this happens if and only if pi of C is also in the code. Now we'll say that G is transitive if whenever you have two coordinates, there is a permutation in the group of symmetries that maps one of the coordinates to the other. And we'll say that it's two transitive if whenever you have two pairs of coordinates, there's a permutation taking the first pair to the second pair in the group of symmetries. Okay. And if you think about it for a little bit, it's not too hard to see that for Reed-Muller codes, the group of symmetries is exactly the set of invertible affine transformations over GF2. Okay. An affine transformation preserves the degree of a polynomial. And now I'm ready to state the result in terms of just the symmetries of a code. So what the result actually says is that for any parameter epsilon and any s larger than 1, if C is a linear code of size 2 to the 1 minus epsilon n, and its group of symmetries is two transitive, then if the group of symmetries satisfies the property that whenever you take a subset of the coordinates of size s log n to the 0.99, then the set of images of that set under the group of symmetries is at least, has size at least n to the s. Okay, so if the group of symmetries satisfies this property, then C will actually recover from epsilon minus order 1 over s fraction erasures. So this is an extremely interesting result to me, because intuitively you think of a good code as a set of strings which are far away from each other, right? Because if there are a lot of strings that are close to each other, then the erasures will sort of confuse the two with a good chance. But somehow in this theorem, there's no statement about how close or far the strings in the code are. Any linear subspace that is symmetric enough will recover from a lot of errors. Okay. And maybe one way to think about it is that the statement proves that if you have a linear subspace with a lot of symmetries, then you can have a lot of strings that are too close to each other. Okay. In some way, in some sense. So that's what we're going to prove. And just to check what this says about Reed-Muller codes, well, as I said, the group of symmetries for Reed-Muller codes is the set of linear invertible affine transformations. If you pick a set, this is a two transitive group, that's easy to check. And further, if you take any subset of the coordinates of size s log n, and log n here for the Reed-Muller code is equal to the number of variables used in the polynomials. So this is s times little n to the 0.99. Then you can show that actually the worst case, the set of coordinates that has the fewest images, is a set of coordinates that forms a linear subspace. Okay, I won't prove this, but you can show that that's true. And so the number of images under the group of symmetries is the same as the number of subspaces of dimension log of Sn to the 0.99. Okay. In general, it can be larger than this number, but if the set S is a subspace, then this is roughly what happens. And now the number of such subspaces you can count as if that's roughly n divided by log of the size of set S, which works out to be n to the power, approximately n to the power 0.99 log S times the number of variables, which is larger than n to the s as long as s is bounded by log n, is smaller than log n. Okay, so for Reed-Muller codes, you can set s to be this large, okay, which will show that the code will tolerate epsilon minus order 1 over log of little n fraction of errors, which corresponds to epsilon minus order 1 over log of big N fraction of errors. All right, so from now on, I'm going to focus on just proving this statement. It just has to do with symmetries of the code. So let me now introduce some notation that will make it easy to reason about what we want to prove here. So we're given a linear subspace, C, okay? And I'm going to define a random variable x, which has n plus or minus 1 values in it, which are all sampled independently. And x determines the set of coordinates that will be erased. Okay. Specifically, the set of coordinates that are erased are the coordinates of x, which are minus 1. Okay. So I'll define c of x to be the projection of c onto the coordinates where xi is equal to 1. These are the coordinates that are not erased. Right? And the claim I want to make is that with high probability, the dimension of c of x is the same as the dimension of c. This is what we'll prove. And this is enough to show that the code recovers from errors. That's because if you think about what the receiver sees here, what they see is an element in c of x. And if this subspace here has dimension that's the same as the dimension of c, it means that every element of c is mapped to a distinct element in cx. Okay? So the receiver can decode the intended transmission if these two dimensions are the same. Now, let me massage this statement, make it a little more precise, and say exactly what we're going to prove. So let's say that for every I, the probability that xi is equal to 1 is a parameter rho I. And I'll think about varying this parameter. So I want to make it a variable. And let's write g of rho 1 through rho n to denote the expected value of the dimension of cx. Okay. Then what we'll prove is that if c is sufficiently symmetric, then for some parameter beta that's very close to 1 minus epsilon, we have that g of beta 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 is at least the dimension of c minus 1 over n. It's very close to the dimension of c. Okay, so for beta that's very close to 1 minus epsilon, the expected dimension of c of x is very close to the full possible dimension. Now, applying Markov's inequality, what this implies is that with high probability, the dimension of c of x is going to be equal to the dimension of c. So if you can show that the expected dimension is very close to the dimension of c, then with high probability, it's going to be equal to the dimension of c, because when it's not equal, it's going to go down by 1, at least. Okay. So that's this is the statement that we'll actually prove from now on. And if it's not clear to you why this is enough to show that Reed-Muller codes achieve capacity, you should pause the video and think about the parameters here and try to make that connection for yourself. All right. So that's the setup. Here's what we want to show. And now let me draw some pictures to explain what we're trying to do and reason about and give you some high level intuition for how we're going to go about doing it. So on the right here, I've graphed the value of g at rho as a function of rho. Okay. So what we want to show is that g, when you plug in 1 minus epsilon, gives you something that's very close to the dimension of the code. But if you think about what this means, the entire plot for g must then look like this, right? Because for higher values of rho, g cannot get any larger. It cannot get larger than the dimension of the code. So the value at higher values has to be about the same, has to be the dimension of the code. And for lower values, if you think about it, the largest possible derivative that g can have is n. Okay? That's something that you should think about. And that means that it has to be the case that this part looks like really a line with slope n. So this is what the entire picture must look like if g passes through this point. And that means if I now plot the derivative of g, then that must look like a step function. It must look like this, right? Its value here must be n, and then it must make a sharp transition to the value 0. So this is what g and its derivative must look like. If it's true that the value of g at 1 minus epsilon is the largest possible value. And indeed, we're going to prove that the derivative of g really does look like this, and that'll be enough to establish that g takes on this value. Okay. So that's our high-level goal, is we're going to show that the derivative of g really looks like this. And as I mentioned, the key tool that we'll bring to bear here is Fourier analysis. Okay? And perhaps the most basic observation in Fourier analysis is that every function that maps plus 1 minus 1 to the n to the real numbers can be expressed as a multilinear polynomial. It can be expressed like this. Okay, so that's the first observation. And now let's see how to use it. So we wanted to understand the derivative of g, and g is, the expected value of the dimension of c of x. Now what Fourier analysis says is that the dimension of c of x, this is a function of x, and it's a real valued function, so that can be expressed as a multilinear polynomial. Okay. And the first claim that I want to make about this is that if you take the partial derivative of g with respect to one of the variables, rho I, then that's equal to 2 times the expected value of the partial derivative of the dimension with respect to the variable xi. Okay. And that claim is actually pretty straightforward to check because the derivatives are all linear. So it's going to be enough for me to prove that this identity holds for monomials of this polynomial. Okay, so let's say we take any monomial, say x1, x2, x3, and look at the expected value of this monomial. Well, because the coordinates are independent, this is the product of the expectations, and that's exactly equal to this expression. And so when I take the derivative of this thing with respect to rho 1, what I get is this expression, which so happens to be exactly 2 times the expectation of x2, x3, which is the partial derivative of x1, x2, x3 with respect to x1. Okay, so this identity works, this holds for each monomial, and therefore it must hold for the entire polynomial. Okay. So that's the first claim, and that means that now I can use the chain rule from calculus to express the derivative of g with respect to rho as the sum of the partial derivatives of g with respect to each of the variables. Okay, so that's the chain rule. And because the underlying code we're working with here is very symmetric, in particular it's transitive, it's actually 2 transitive, all of these partial derivatives must be the same. Okay. So if that's not clear, you should spend a few minutes to think about that and verify it for yourself. So this sum is equal to n times the first partial derivative, which is equal to 2n times the expected value of the first partial derivative of the dimension by our claim here. Okay, and basically the same reasoning leads to the result that the second derivative of g can also be expressed like this. Okay. All right, so that's the first observation. And now let's really push this to see what it says. Let's try to understand the partial derivatives of the dimension. So here I've rewritten what I said on the last slide, and I'm going to call this function 2 times the partial derivative of the dimension. I'll call that the function f. So that's a function of x. Okay, so the first observation I want to make here is that because this function, the dimension, because of Fourier analysis, this dimension is a multilinear polynomial. And for a multilinear polynomial, its partial derivative can be expressed using a discrete operation. The partial derivative of this polynomial with respect to x1 is the same as evaluating the function when you plug in 1 for x1 minus evaluating the polynomial when you plug in -1. And then dividing the difference by 2. Okay. So this polynomial here is exactly the partial derivative of this polynomial with respect to x1. But the dimension is very nice as a function. When you flip a coordinate from -1 to 1, the dimension can change by at most 1. Okay, either it doesn't change or it changes by 1. And so the function f of x has to be a function that takes values in 0 or 1. It's either equal to 0 or equal to 1. So that's very nice. There are lots of consequences of that. It means that, first of all, the value of this derivative here has to be a number between 0 and n. Okay, it has to be between 0 and n. That's the first consequence. The second consequence is, if you think about this expression, you see that f of x is monotone and non-increasing. It cannot increase. That's the second consequence. And moreover, f enjoys all of the symmetries that the underlying code enjoyed. And finally, it must be the case that dg over d rho, for all these reasons, is monotone and non-increasing. So it's a function, the derivative over here is a function that's bound between the two boundaries of the step function. It's monotone and it's non-increasing. So we're getting closer towards showing that this really looks like a step function. We'll complete the proof by using Fourier analysis to prove a really powerful claim. Okay, and that's what's written here as the key claim. And let me explain what it says. The claim basically says that the derivative of g must make a very sharp transition from being very close to n to being very close to 0. And how, let me explain how that's actually captured. So let's define alpha to be the point at which the derivative of g hits the value n minus 1 over n. And let's define beta to be the point at which it hits the value 1 over n. What we're going to show using Fourier analysis is that beta minus alpha is bounded by order 1 over s. It's small. Okay. And now let me explain why this is enough to finish proving that the code achieves capacity. It's because on the one hand, if you look at the dimension of the code minus g evaluated at beta, then this difference must be equal to the area under the curve in this part of the picture. The area under the curve here. And this area is bounded by 1 over n by the choice of beta, because the derivative is at most 1 over n in this entire region. Okay. So this is at most 1 over n. That proves that g evaluated at beta is at least the dimension of the code minus 1 over n. The second observation is that if you look at the dimension of the code, that's at least as large as the area under the curve in this part, from 0 to alpha. And by the choice of alpha, that must be at least alpha times n minus 1 over n. But alpha and beta are close by the claim. So this quantity is at least beta times n minus something that's order n over s. Okay, and if you divide this equation by n, you get that beta is at most 1 minus epsilon plus order 1 over s, which establishes this part of our goal. Okay, so once we've proved this key claim, we'll be done. So that's the only thing we need to do. And to do that, we really need to use now deeper ideas from Fourier analysis. So let's do that next. So in our application here, we're using Fourier analysis with a distribution that's not uniform. Okay, the coordinates of x are not sampled uniformly. They're all biased bits. So to understand what's happening here, we need a slightly atypical way of using Fourier analysis. Let's define the functions Li like this. Okay, this takes into account the distribution of each bit xi. And this choice of Li ensures that the expectation of Li is 0 and the expectation of Li squared is 1. Okay. And you should check that those things hold if it's not clear to you immediately. So now given any function f, I can, f, we've already talked about how it's a multilinear polynomial. I can write it using the linear functions Li that I just described like this. And let's do that. And once you express f in this way, you can see that the 2 norm of f, which is the expectation of the square of f, the square root of the expectation of the squares of f, is equal, the squared 2 norm is equal to the sum of the squares of the Fourier coefficients that we obtain. Okay. This fact, which is the analog of Parseval, is a simple consequence of plugging in this expression here and using these two observations. Okay. So the 2 norm of f is the sum of the squares of the Fourier coefficients. The variance of f corresponds to the sum of the squares of the non-trivial Fourier coefficients. So those are some basic facts that I will not prove. You should check them for yourself if they aren't clear to you. And then next, I want to explain some even deeper results which concern Boolean functions. So let's say your function doesn't map into the reals, but it's actually Boolean. And this is exactly corresponds to the kind of f we're interested in studying. For a Boolean function, a really deep result is that every such Boolean function must have an influential variable. So let me say exactly what this means. Let's write fi of x to denote the ith partial derivative of f, okay, which is this expression based on how we expressed f here. The influence of f, the ith influence of f, is the squared 2 norm of fi, okay, which is equal to this expression. Now it's easy to see just from this formula that the sum of the influences must exceed, must be omega of the variance of f. And that means one of the influences must be at least 1 over n times the variance. But a really nice result is that you can do better when f is a Boolean function. When f is Boolean, one of the influences must be at least omega of log n over n times the variance. And you can do even better when f is a function that is highly symmetric. If G is the group of symmetries of f, this set of permutations. And this group satisfies the same conditions as what we asked for the group of symmetries of the code, these conditions. Then you actually get that there will be a coordinate of f whose influence is omega s log n divided by n times the variance. So you get an even larger, even more influential variable. Okay. And in fact, the function we defined does satisfy the assumptions here. Its group of symmetries does satisfy these assumptions because its group of symmetries is the same as the group of symmetries of the code. Okay. So I will not prove any of these results here. They're very interesting, and I will take them as given. At some point in the future, I will make a video explaining the proofs of these results as well. So stay tuned for that. But for now, I'm going to use these facts from Fourier analysis to actually reason about the code. So if you remember, the only thing we have left to do is prove that beta minus alpha is order 1 over s. That's what we need to show. The gap between these two parameters is small. And let me recall some formulas that we've already shown. So we've shown that the derivative of g is n times expectation of f. Okay. And the second derivative we expressed as something that's omega n squared times the expectation of f2 of x. This is what we already showed. Now, a nice observation here is that because f is Boolean, f2 of x also can only take on one of three values. It can either be perhaps half, 0, and minus half. But f of x is also monotone, which means that the derivative can actually take on only the values 0 and minus a half. 0 and minus half. And that means that you can express the expected value here as something proportional to the expected square of f. Okay, because this square is equal to 1/4 when this number is a half, and it's 0 when this number is 0. So it's you can express this as a half times the other number. Okay, so I can replace in this expression the expected value by the expected square of f2, and that's exactly the second influence of f. The second influence of f is what's written here, which by this theorem must be large because f is too transitive, and so all of its f is transitive, and so all of its influences are equal, and so this influence in particular must be at least s log n over n times variance, and plugging that in here, we're left with this expression. The magnitude of the second derivative of g must be large. It must be at least Sn times log n times the variance of f. Okay. So that's great because we showed that the second derivative, the slope here, must be large. And now it's just a matter of doing a little bit of calculus to prove that if the slope is large, alpha and beta cannot be too far apart. And that's pretty straightforward, but let me show you how to do it. So it turns out it'd be helpful to understand the derivative of this formula. So let's consider log of the derivative of g divided by n minus the derivative of g. If you do some calculus, I'll leave it to you to work it out and check for yourself. But what you get is that the derivative of this expression is n over the derivative of g times n minus derivative of g times the second derivative of g. Okay. This is a straightforward calculus. And now what you see is what you have here can be written as 1 over n times the expectation of f minus 1 minus times 1 minus the expectation of f, which is 1 over n times the variance of f. Okay, so this formula is actually basically chosen so that here you get the variance in the denominator. And now let me show you why that's useful. Because if I evaluate this formula now at beta, this is what I get. And if I evaluate the formula at alpha, this is what I get. Okay. Both of these terms here are order log n. Okay, so their difference is bounded by log n. On the other hand, their difference is equal to the integral from alpha to beta of this quantity. Okay, so say, okay, by what we showed here, this difference is equal to the integral of this function. And it's been set up so something nice happens because we know that the magnitude of the derivative exceeds Sn times log n times variance. So you have a cancellation. What you're left with is that the derivative is at least S times log n in magnitude everywhere here. And that means that 5 log n must be larger than S log n times beta minus alpha. And this proves that beta minus alpha is order 1 over S. So it's a really beautiful proof with some very nice ideas, and I hope you enjoyed it.